All right, welcome everyone. My name is Daniel Moyer, sales support trainer here at Briggs & Stratton Energy Solutions. Today we're going to talk about AC and DC coupling. We're going to define those terms. We're going to talk about how certain situations maybe necessitate one or the other. This is approved by NABCEP, so I will be issuing continuing education credits. At the end of this presentation, my email will pop up. Email me your full first and last name, and then I'll go ahead and issue you the credits. Additionally, everybody who's here will get a copy of this slide deck and also a copy of this recording. Lastly, the chat is disabled, but the Q&A is open. So if there's any questions along the way, please pop them in and we'll take a look. Let's get started. You know, I realize in this energy storage industry that a lot of people are selling batteries, a lot of people are selling inverters, and it's easy to sell boxes that people put on the walls. But what really matters also is the company that's selling you these products. Are they going to be around in the 15 or 10 years that they're honoring a warranty? Are they going to have knowledgeable, local to the US based tech support that's responsive? Are they also going to be able to have that engineering support? And I'm really proud to say Briggs & Stratton does hit all of those marks. Another thing Briggs & Stratton does is bring some name brand recognition to your company, to your offerings. I found out I was going to be working for Briggs & Stratton after they bought SimpliPHI Power a few years ago now, and I instantly thought about my Briggs & Stratton story of mowing a lawn in the 1980s in the heat of the California sun and doing my first oil change on an engine. And when I had an opportunity to go visit Milwaukee, home of Briggs & Stratton, get off the airplane, get in an Uber, in the distance I could see this giant water tower that had Briggs & Stratton on it. And I realized what a large company, what a historic company that has a legacy of manufacturing Briggs & Stratton was. So I'm really proud to be working with this company and knowing that I'm honoring a legacy of a company that's been around for a long time. That's the picture of the water tower and the headquarters there. And there is an opportunity if you want to go see that next week, next Monday, just a few days from now, we're going to be hosting a solar and battery energy storage summit at our headquarters. We're going to not only have training opportunities from the likes of Ryan Mayfield, but also other participants will be showing off their equipment. We're going to have a tour of the museum. We're going to have a tour of our power garage, our training lab. It's a free event. Breakfast, lunch is included, and we're also going to have transportation back to the convention center at the end of the day, where NABCEP is being held that week. So if you're interested, scan this QR code, just email me, and I'll get you a spot, reserve you a spot. So hope to see everybody next week. Safe travels if you're coming out to NABCEP. We sell batteries. We sell a great battery, if I don't mind so saying. The SimpliPHI 6.6 battery is a stacking battery. Each module is 6.6 kilowatt hours, and it stacks up to 20 kilowatt hours in a single stack is what I'll call it. And then we let you, the installer, have the inverter of choice. We have a number of inverter partners. Historically, we've worked with SolarArc for a long time, but we now offer EG4, GrowWatt, MegaRevo, and soon to be Solus. So the idea is that we provide the batteries, and then you, the installer, choose the inverter that you like of choice. And in a lot of ways, that's what we used to do in this industry. We would have a certain battery brand, a certain inverter, maybe even a different charge controller, panels from a company, racking from a different company. And there's still some advantages to that we're offering you that ability to choose the parts and the pieces that you work with. We're not simply going to say, go talk to the inverter if something happens. Our tech support team, the sales team are very knowledgeable about all these other inverters, and we're going to help you navigate these challenges. So excited to be partnering with all of these great inverter companies. Also notice in the screen here is our energy track. It's an optional monitoring gateway that allows you to have more visibility on what the batteries are doing. And additionally, it's allowed you to update firmware to the batteries. It's optional. You can use it as a service tool, but keep in mind that a lot of the inverter partners have their own monitoring apps as well. So let's just kind of set the stage here really quickly, and then we'll dive into the AC-DC coupling. What is an energy storage system? So in the center of the screen is a hybrid inverter. This example is a solar. We have a grid that can be used to charge the batteries when the grid is operating, keep the battery charged. When the grid goes down, within milliseconds, the inverter will recognize that, disconnect us from grid, then using energy stored in the batteries, power the home's loads. Notice we don't have any generator or solar in the picture. It's surprising to me that there is more and more opportunities where we can just have battery backup. Of course, the battery is only going to last as long as it has juice in the battery. And then when the battery runs down, the inverter will recognize that and then do low battery cutout and turn off the loads. We, of course, can add solar. We can either do DC coupled solar or AC coupled solar, and we'll get into that here in a second. And additionally, we can also add a generator. And that's been an example too, where you can have a battery, you can have a generator and no solar, and we can program that inverter. When the battery starts to get low, it will automatically start the generator. While the generator is running, it will take over the home's loads and then be able to recharge the battery at the same time. Interestingly, you see the arrow going between the grid and the inverter is bidirectional. If the batteries are full, the home's loads are satisfied, and there's still excess solar production, we can send it back to grid in states and municipalities that will offer net metering. A lot of those net metering policies are going away. Some examples, you're not even allowed to backfeed to the grid anymore. So what that means is if we are in a situation where we're not getting that one-to-one net metering credit, we're not going to want to send that excess solar back to the grid because we're getting paid almost nothing for it. We're going to want to store it in the batteries during the day when solar's producing and then discharge it up to the home's loads. That's going to be key to see a financial return on any solar photovoltaic systems. It's interesting to see how this is changing the landscape of how grid-tied solar is working. If you are in an area where net metering has gone away, put it in the Q&A. Let me know how you're repositioning your energy storage systems as well. Let's kind of break down what does it mean for DC coupling and what does it mean for AC coupling. What we're talking about in a lot of ways is DC is produced by solar panels. Batteries store energy in DC. Our home's loads use AC. So back in the day, how we used to do it is we would have solar panels either strung together in series and parallel that would go through charge controllers and charge up the batteries. Only when we needed to use that DC power for AC loads would we use an inverter and turn DC into AC. So that's kind of the bottom one, right? Coupling DC power from PV array with the charge controller in order to charge a battery bank directly. And then only when we need to use it do we turn that DC to AC. Every time you switch between DC and AC, AC and DC, you lose something. You lose a little bit. AC coupling. Now, AC coupling is when we take a DC coming out of a solar module, we turn it to AC, we send it AC down the roof, and then we turn it back into DC with like a battery charger, essentially, and we charge up the battery. Then we have to turn it back into AC when we want to use the home's loads. And like I just said, it's wasteful to do that, to have to switch back and forth. But there's examples when that actually might be the way you want to do it. And one great example is when we're retrofitting an existing solar photovoltaic system that may have micro inverters or may have a string inverter. We want to leave it alone. We don't want to get up on the roof. We don't want to have to bring that entire array back up to the modern codes. We leave it there and we simply bring the AC down off the roof, feed it into that Solarc or that EG4 or any of those other hybrid inverters, and use that AC to charge the battery using a battery charger, and then turn it back into AC when we need to power the home's loads. So that's essentially kind of the takeaway is DC coupled is when we're adding new solar, and we're going to want to keep it DC coupled because it's a little more efficient. It's usually a little less expensive because we're not having to buy another string inverter or micro inverters, and we're charging the batteries. AC coupling is usually referring to when we're coming into a retrofit system and we're able to take that existing array, not touch it, and charge up the batteries using a battery charger. Then when we need to power homes loads, we turn it back into AC. Now, there is some examples and some other products on the market that don't have charge controllers. So in those examples, you would AC couple on a new install as well. And Enphase is an example of that. Well, let's talk a little deeper about DC coupling right here. We got a nice picture of a ground-mounted photovoltaic array on the right-hand side there. And we're taking that DC and we've run those panels either in series, which is negative, positive, to build up that voltage. And we feed that into a MPPT charge controller. And that charge controller needs a certain voltage to come alive. And a lot of them are usually around 150 volts. So by running those modules in series, we're able to build that voltage up and get those MPPTs to come alive. Usually the higher end of the voltage range on these MPPTs is around 600 volts. Back in the day when we had 36 volt modules, which is around 18 volts nominal, 36 cell, I should say, or 72 cell modules, they're pretty low voltage, but what we've seen in the industry is a lot of 60 cell modules and 60 cells, right? And each cell is about 0.5 volts, so we're around 30 volts. So the voltage of each of the panels is going up, and what that means is that we need fewer in series to create that voltage necessary to get the MPPT to come alive. Now, we don't really need to take too much of that away because there's a lot of tools like Aurora or Open Solar or even some of the inverter partners that can automatically string together the modules you've placed on a roof so that you know that you're getting the proper voltage range to make these charge controllers in these hybrid inverters work correctly. Keep in mind, you can also parallel up the strings, which would build amps and not volts. We're going to get into it in a second, but understand that these solar modules on the right-hand side have a couple of ratings. One of them is volts open current, open circuit. So what that means is that if you just took a solar panel and you had the two electrical leads coming out the back of the panel and you put your multimeter on it and you were simply to measure the voltage, that would be the voltage of the panel with no current, right? Voltage open circuit. You could also do amps short circuit, which is you take that same multimeter, you usually got to move your little lead over to the amp side, set it to measure DC amps, and as long as it doesn't exceed the amp rating of your Fluke multimeter, you can be able to just measure the amps. You're seeing all of the amps coming out of that panel with no voltage. But keep in mind that there is volts at maximum power point and amps at maximum power point. There's on the back of the panel, there's a little rating that says if you amps times volts equals watts. And if you get those 2 points together, you're going to get the maximum amount of power in watts out of that solar module. And without a load, you're not going to be able to measure that. That's going to come into play here in a second as we talk about the IV curves of some of these solar modules. Keep in mind that irradiance, or the amount of sunlight hitting the panel, affects the amps coming off of a solar module, and temperature affects the voltage coming off of a solar module. The colder it gets, the voltage goes up. Hotter it gets, voltage goes down. More sun, amps go up. Less sun, amps go down. You know, another thing to keep in mind as I'm looking at this picture on the right-hand side is I see some shading on one of those solar modules in the bottom left-hand corner. A lot of these panels do have bypass diodes in them, which allows a couple of cells to be shaded and not affect the production of the rest of the panel and the rest of the modules run in series. But if we do have a number of modules that start to become shaded and they're all run in series together, it will start to affect the entire array. Whereas if we run them in parallel, we don't see that happening because they're not affected by the parallel configuration. There are some optimizers that can be used to mitigate that, and we'll talk about that here in a second. So again, we're just sticking with fundamentals. We're going to get more deep in the conversation here in a second, but you got a solar cell that comprises a solar module, and then that solar module is put into a solar array or a solar system. Now, I'd love to hear your guys' input about some of the technology. This is kind of an old picture because there's a lot of half-cut cells in this. And I see a lot more cells per module now in some of the future ones that I'm starting to see in the market. But again, this is what we're talking about. When you got the multimeter here and we're measuring all amps, no volts. Again, don't blow the fuse in your meter, check the amps. Or we're measuring all volts and no amps, right? There's 0 watts here and there's 0 watts here, 0 power. And at some point here along this curve, and it's usually right here at the knee of the curve, we're going to get the maximum power point, right? At where the amps times the volts, the highest we can get the amps, the highest we can get the volts results in the most power. And you can almost think of it as the area underneath this kind of peach-looking curve right here. When we have different types of charge controllers, and we'll get into that, it's going to affect how much we're able to harvest right here. So a charge controller. And a lot of that solar arc that I showed you before, the EG4 or those other hybrid, the Mega Revo, a lot of those hybrid inverters have the charge controllers built into them. They have the generator port built into them. They have the inverter, battery charger built in. That's called their hybrid inverters. It's all built in. Kind of back in the day, and not that long ago, to be honest with everybody, we would have separate charge controllers and separate inverters and separate components that comprised the system. But what these charge controllers do essentially is prevent the battery from being charged from a charging source. And it's almost always been PV recently, but back in the day, we've had micro hydro or even wind power can be a DC charging source. We want to make sure that we don't overcharge the battery by putting too many volts. A 36 cell module where all of the cells in that module are run in series produces around 18 volts. Well, if we're thinking about a 12-volt battery, we don't want to be putting in that many volts. We could damage the battery. So what we're going to do is we're going to step down that voltage to the appropriate charge voltages specified by the battery manufacturer. That's what a charge controller does, is that it prevents the battery from getting too many volts from overcharging the battery. It can also prevent too many amps. All batteries have a certain C rate or a rate at which the batteries can be charged. And that, again, that's specified by the battery manufacturer. And we can go into these charge controllers and adjust the charge amps so that we're not charging the battery too quickly on amps. There's two fundamental types of charge controllers on the market. One's called MPPT, maximum power point tracking, and the other one's called PWM, or pulse width modulation. Now, you know, I almost hesitated to even talk about PWMs in this talk because they're becoming less and less common. Back in the day when we had expensive charge controllers, MPPTs, a strategy was to go with the less expensive PWMs. Now, PWM charge controllers aren't as efficient, but they were a lot less expensive. Well, I just went on to Amazon this morning and realized that these MPPT charge controllers have dropped so much in price that they, I mean, $20, $40 for, you know, some non-name brand maximum power point trackers are available out on the market. So they're so cheap that why even bother with PWMs anymore? And that's true. Almost nobody's using them. If you're still using a PWM charge controller in a system, a modern system, please put that in the Q&A and tell me why you're still doing that. And I could think of maybe some of those Morningstar ones that I liked, or Focus makes some great ones too. But the reason I left it in is it allows me to kind of demonstrate the differences between the two and talk about the efficiencies and call it out. So we'll show that here on the next slide. But what an MPPT does is it detects the output voltage of the module in real time and then can essentially drop the voltage while increasing the amps so you're not losing anything. Again, volts times amps equals watts. And it can essentially ride the knee curve that I showed you earlier to maximize the production. MPPT, PWM charge controller doesn't do that. So let's go back to our example. We got a 36 cell module. It's outputting 18 volts, but we're trying to charge a 12 volt battery, let's say at 13 volts, right? We want a little bit higher voltage to charge up that battery, 13.5. As soon as we connect that solar panel to the battery, the battery is going to pull down the voltage of that solar panel. Remember, the panel, that 36 cell solar module, has a maximum power point of around 18 or so. So it's going to get the most power out at that higher voltage. But when we put it to a battery through a PWM charge controller, it brings the battery, the solar panel voltage down. And so we're not getting the maximum power that we could possibly get out of that solar module. And how a PWM works is essentially it's like a switch inside of it. And it rapidly opens and closes. So anytime you see this blue here, that's when the full voltage of the module is allowed to pass through down to the battery. And then it closes and opens and closes. And as the battery and the voltage of the battery starts to get more and more, those pulses that allows that voltage to pass through down to the battery become shorter and shorter because we don't want to overcharge the battery. And at some point, it'll completely shut off as well. These are great for smaller systems. I mean, look at it's Morningstar made that sun saver up in the top right-hand corner there. You see, you connect the solar panel into the solar. You got your battery there that's in the middle part, and this is a 24 volt. And then on the right-hand side, we got our loads. And what's cool about this is that this one actually does also built into this have what's known as a low voltage battery disconnect. As I was talking about earlier, that if the battery voltage starts to get too low, we don't want to continue to drain the battery or else you'll damage the battery. So this one has a low voltage battery disconnect built into it. That's why it's called the SunSaver 20L. And it will turn off the loads once it gets to a set point, maybe 12 volts or 11.5 volts or something around there. So we're going back to the MPPT, and essentially, as we talked about earlier, is that there's a calculation where a solar module at a certain volt and a certain amount of amps produces the maximum amount of power or watts that come out of this. And we want to find this point right here. And this MPPT charge controllers are constantly kind of doing that calculation and can adjust the voltage and the amps to ride that kind of knee. So if we have that 18 volt panel, it's not going to have to, it's going to drop down that that voltage, but it's going to be able to raise up the amps and find that balance. So we're getting the most power, maximum power coming out of that solar module. A couple other advantages of MPPT charge controllers is, I keep talking about that 36 cell module because it's 18 volts and it allows us to charge a 12 volt battery, right? They're different, but they're not that different. With MPPT charge controllers, we're not constrained by the voltages coming off of the solar array because we can adjust that as we see with these MPPTs. So now I can have a solar array of, let's say, those 36 cell modules, like maybe 10 of them in series. So now instead of 18 volts nominal, I have 180 volts. Well, that's okay. And these MPPTs allow us to do that and allow us to drop down that voltage, increase the amps to be able to still charge up a 12-volt battery bank. And by also running them in series, we're able to build up that voltage so that usually in the morning, when there's not a lot of sun, the voltages of a solar module aren't high enough to cause that charge controller to come alive. Remember, I talked about that startup voltage. Well, when we have a lot of modules in series, we're able to build up that voltage so that we're able to get that charge controller to come alive earlier in the morning and stay operable later into the afternoon as well. So, and also if we have shading, right? So these MPPTs really help when we have shading or that low sun in the morning and in the afternoon as well. So it's interesting too that some of the DC optimizers, say from SolarEdge or even from Tigo, use some of this similar technology to optimize these production of the solar array. Let's take a look. Gail, thank you. I'm glad you're here. Thank you for the comment. An anonymous attendee, 23 years ago, they had installed two Morningstar TS60s, right? Those are 60 amp charge controllers, I believe. They're still both working. I mean, these things were workhorses in a lot of ways. They've been doing a lot, and you still have that old Xantrex 4024, which is I think 4024 stands for a 4,000 watt inverter at 24 volts. So anyway, there's no reason to change a lot of that equipment. And that kind of goes back to the idea that we're going to talk about here when we're retrofitting systems, that if it's working and we still have a SolarEdge inverters, let's keep them on there. So, you know, we talked about DC coupling of solar arrays, but I kind of like the idea of talking a little bit about DC coupling batteries. So in this example, we have a solar array on the right-hand side. We have a charge controller from Victron, and we're feeding it down to some batteries on a DC bus. And then we come up to this Victron inverter that's allowed to power AC loads or even use grid to charge the batteries or even send back to grid. And this is really common even on off-grid homes, is that everything's AC in the homes. In a lot of ways, there's still an opportunity to do DC loads. We could have DC water pumps. We could have DC light bulbs. And it's really interesting. I found this article in an NREL website talking about the future of our home's energy usage, and that there may actually be an opportunity to revert back to DC architecture in the home. Remember, we said earlier that anytime you change from DC to AC or AC to DC, you lose something. And with the advent of these, USB-C plugs that charge up our cell phones, some of those can supply up to 100 watts. And wouldn't it be cool to see a day where instead of plugging your lamp on your nightstand next to your bed into a AC outlet, maybe you just plug it into a USB-C outlet and you have a DC light there, right? These lights are all LEDs anyway, which require drivers. So it's really interesting to see this, and even the idea that you can send a lot of power over Ethernet cables as well. So again, everybody will have a link to this article, and take a look at it if you want. So we're kind of breaking down that other schematic we had earlier. We got some solar modules on the left there, all run in series. So we're building up the voltage necessary to make that charge controller, which is inside that Solar 12K, come alive. Then we can use that DC to charge up our batteries at 48 volt nominal. And then we can turn that DC back into AC we only have to change it once to power that load center and that microwave that you see up on the top right there. I'm also demonstrating the ability of a generator. I put in this disconnect there between the solar modules and the Solarc. That may be necessary, but keep in mind that the Solarc actually has a PV disconnect built into it, but your jurisdiction might want that depending upon if they don't think that the shutdown in the Solarc is in a readily available location as well. This is what it looks like in a lot of these hybrid inverters. I'm showing you an example of what it looks like inside of a Solarc 15K, but a lot of the Mega Revos, the EG4s are the same. What made these hybrid inverters really popular is the three AC ports, right? We got our grid port on the right-hand side that allows AC to come in from grid. We have the load port that allows loads to be backed up if the grid goes down. What's key here, and this is what we're going to get into for the AC coupling side of things, is that it has this third port, this gen port. And this gen port, and you'd think gen made for general, but or generator, but it actually means general. This third port is what really made these hybrid inverters powerful and flexible. We can either use this to feed AC in from a generator to charge up batteries and support loads, or we can use this third port, this general port, to feed in AC coupled solar to charge up batteries and support loads. Some of these differ between inverter companies, but it can also be used as an output to act as a smart load port, which can be turned on and off based on the state of charge of the battery, right? Load shedding. We got our battery CAN bus. That's where we communicate with our battery. Our accessory pinouts, that's where we have things like CT connections and two-wire signal to start to generators. Paralleling comms is where we would parallel up multiple inverters if we have them. DC breakers and DC battery connections, that's where we bring the batteries in. DC PV inputs. It has charge controllers built into this. This is where we're going to be able to DC couple solar. In this example, we have 3 MPPTs, and each of these MPPTs has, you can see, 4 little orange tabs. And what that allows us to do is to run modules in series. And if we need to, we only need to use 2 of those orange pins. But if we have, say, some modules in series and another set of modules in series, instead of using our little MC4Y adapters, we can create parallel connections inside of an MPPT here. Staying on the topic is that, why have 3? Well, if we have, say, some solar modules on a west roof and some solar modules on an east roof, as I explained earlier, if we're getting shading or the sun's not hitting an array, it affects the production of the array that is in the sun. So by keeping them on separate MPPTs, charge controllers, we're able to still have one array operating in that morning, capturing the west sun, and then that afternoon sun on the east array is able to capture that, and we're not having one array dragging down the production of the other array. So that's why we have multiple MPPTs, and if we even had a south array, we could put that on the third MPPT there as well. So AC coupling, traditionally, it's when we have an existing array, and we want to go ahead and add that into a new battery system that you're putting on the wall. So we already talked about how it turns from DC to AC. AC has to be put into a battery charger and then be able to charge up the batteries. You see this picture on the right. I see a Fronius up on the top left there. I believe that's probably the string inverter. And then we have a Victron hybrid inverter, or an inverter that can take in that AC and then be able to charge up those batteries. We usually call the string inverters, like the Fronius, all it can do really is take the DC off of the solar panels, turn it into AC that can either be sent to the loads or sent back to the grid. A hybrid inverter or a battery inverter can do the same thing. It can take in AC from a generator, from AC coupled solar, but it also has the ability to charge up the battery. And it also has what I call a transfer switch, or a MIDI, an MID, to be able to isolate us from grid. And I'll show another example here in a minute that will speak more to that. And again, we looked at that other example, that third port, that gen port, whether it's AC coupling coming in from, AC coming in from AC coupled solar, or whether it's a generator producing 240 volt AC, the hybrid inverter doesn't care. It's just AC coming in that can be used to support loads or charge batteries. One thing it does care about is if we have that solar, for example, and the grid is down, the AC coupled solar is producing, and we're feeding that AC coupled solar into the gen port. Once the batteries are completely filled or topped off, right? Their batteries are charged, and the loads are kind of satisfied by the AC coupled solar coming in, we need to be able to shut off that AC coupled solar. Remember, with DC coupled, with charge controllers, like that PWM or the MPPTs, once the batteries are full, the charge controller can shut off the current. It can disconnect the solar from charging the batteries. But with these AC coupled systems, they're going to want to keep producing as long as it sees grid available, and that's being formed by that hybrid inverter. So the way we shut off AC coupled solar is that the hybrid inverters know when the batteries are full and can then say, I want to turn off AC coupled solar. And what the inverter can do, hybrid inverter can do, is it can start to adjust the AC sine wave that it's generating so that the string inverter or the microinverters will recognize that increase in frequency and say, okay, the frequency is starting to go up. I need to start shutting myself down. And that will prevent the AC coupled solar from overcharging the battery. In normal AC, in a normal string inverter, remember I said it can go to loads or it can go back to grid. So if the grid is there, it doesn't matter. It doesn't need to ever shut down because it's just going to start pushing it back to grid. And here's an example I'll show you. So this is a bread and butter Enphase system that you'll see. You got solar modules. Underneath each solar module is a IQ7 or an IQ7 Plus, or maybe an older one like an M250 microinverter. DC gets turned to AC. All of these microinverters are outputting 240 volt. They're all run in parallel, and then they're sent down to a combiner box here. And that's all this Enphase box is here, really, is just a breaker box with some monitoring in it. This AC then gets landed on a breaker inside our load center of our home, usually at the bottom, unless it's like a center fed box. And then it's sent back out to grid. If grid is lost, by design, these microinverters shut themselves off within milliseconds. It's called anti-islanding. Because if the grid is lost, and here you are with your solar panels producing AC, and they're sending power back to the grid, you're energizing the power grid from your home, and there might be a electrical utility worker on your street trying to get power back into your neighborhood, thinking that the power is off, but here you are backfeeding the grid. So by design, these microinverters and string inverters shut themselves off within milliseconds, and so they're not backfeeding the grid. And what we do when we AC couple a system is we take that output from the Enphase combiner, again, it's just really a load center, and we feed that into the gen port on our Solarc that we talked about earlier. So now, if the grid goes out, the Solarc recognizes that, and within millisecond, it disconnects us from grid, but the loads don't shut off in the home. It uses energy stored in batteries to create a grid in the home. What it also does is forms a grid so that the microinverters or the string inverters never see the loss of utility. It sees the AC sine wave being formed by our solar arc inverter and think that utility is still there and continues to output. Again, if the batteries start to get full, the solar arc is smart enough to start to adjust that sine wave to then curtail AC solar production. This is the key, right? String inverters, microinverters shut off the second they see grid go away. With the solar arc, because the transfer switch or the MID is built into the solar arc and it's able to form a grid using energy and batteries, all of your home's loads stay on and all of those micro or grid tied inverters stay on. I'm just looking at Jesus. The string inverter needs to see 240 volts in order to produce AC power. Is the battery inverter going to provide that voltage required through the gen port to allow the string inverter to start producing power? Yeah, so that's a good point. So you remember earlier I said that you could feed AC power into the gen port and it'll charge up the batteries. But what the solar arc is doing, it's actually still providing AC output in some ways so that the string inverter or the microinverters recognize that grid is still there. Great point. This is what it looks like on the right-hand side here. So we came out to this house. This is solar edge, so there are optimizers up on the roof, but it's still DC coming down off the roof through this conduit. You can see they got all their warning labels from PV labels. We have two solar edge inverters that are feeding into this load center. And if I had to guess, there's probably two 20 amp breakers in here that are the outputs of both of those solar edge inverters. And then they're either lug feeding or there might be another breaker here that's flowing down through this conduit right into that solar gen port. And then we got two great looking SimpliPHI 6.6 batteries here. Again, these could be a stack of one, stack of two like you see here, or even a stack of three as well. One thing, and I'll address this now, is that we also have this red switch here, and this is a rapid shutdown switch. If the power goes out, the solar arc forms a grid and is able to power the home's loads. It also forms a grid so the solar edge inverters see the grid being formed by the inverter and continue operating. Well, what happens if your house is on fire? Try not to think about it too much, but the fire department shows up. The first thing they're probably going to do is turn off the gas to your home and turn off the electricity to the home by flipping the main breaker in the home, or maybe taking their axe to the meter socket in the meter. They think that they've just shut off power to the home and are able to go in and fight the fire. But really, all that did was make the solar arc think that there's been a loss of utility, and the solar arc is going to then use energy stored in batteries to power the home's loads and keep all of those solar panels alive up on the roof. So we have to have a rapid shutdown button that you twist or push that then tells the solar arc that you need to shut off all of the AC coming in and out of me, and then also shut down any rapid shutdown devices that may be up on the roof. And I'll get into that, how that works here in a second. And I guess I'll do it right now. How do you turn off a solar panel? The only way I could think of as turn off a solar panel is to maybe put a blanket over it. It's always going to produce power coming off the leads. But the code says that we need to shut down the modules at the module level. So we do this in a couple of ways. Microinverters is one way, but these rapid shutdown devices, and in this example, I'm showing some Tigo TS4F, I believe. And these ones are a little different. They actually can take two modules in per optimizers, but a lot of times we just do one optimizer per module. These solar panels produce DC. They flow through these rapid shutdown devices, which can also be optimizers, down into the charge controllers in our solar, and then charge up our batteries. The solar is generating a 12-volt output that's being sent to this TIGO transmitter that's sending what's known as a keep alive signal through the PV wires up to the rapid shutdown devices and telling those rapid shutdown devices to stay on. These rapid shutdown devices are normally closed, but if they see a signal being generated, they'll open. No, they're normally open. They'll close if they're seeing the keep alive signal, right? They're closed, they're sending power down. If you push this rapid shutdown button that's on the side of the house, that 12-volt supply coming out of the solar will cut power to our TIGO transmitter, which will then tell these optimizers or rapid shutdown devices to open and stop sending DC power down the roof. Sometimes these TIGO transmitters and other types of them aren't powered by the DC off of the solar. They're actually being fed DC by a power supply that's located in this backed up load center. But if you press this button, all AC coming in and out of the solar is going to shut off, which means that this panel is going to go dead, which means that the power supply that was located here is going to go dead, in turn, cut the transmitter, turn off the rapid shutdown devices. In AC, we still have a rapid shutdown button and we have microinverters. Remember, if we push this rapid shutdown device, all power coming in and out of that solar on all three ports goes dead. And we recall that the end phase or the string inverters, whatever it may be, is looking for the presence of grid on that gen port. And as soon as we hit that rapid shutdown button, the gen port goes dead. The microinverters recognize that as a loss of utility and will also shut themselves off. Now, I know we're kind of coming up on time, but I did want to address one thing here, and this has really nothing really to do with a lot of the existing systems, but with one exception here. Imagine you got your main electrical panel at your home, and you got a bunch of breakers in it, and you got a main breaker, you got grid feeding this load center full of a bunch of breakers. Maybe it's rated for 200 amps. And the breakers are all connected to a piece of metal in there. It's called a bus bar that's rated for 200 amps. So for whatever reason, you turn on everything in your home and you're using 200 amps and you're flowing 200 amps out of this breaker panel. If you exceed 200 amps, that breaker is going to trip. It's going to shut off and protect those metal plates, that bus bar inside the load center. But what if you come along and you got a 200 amps coming in and you're now back feeding a breaker at the bottom of this load center with, let's just say, another 100 amps. It's possible that if you turned on everything in your home, you could be drawing 200 amps from grid and you could be drawing 100 amps from your solar system, and you could potentially cause a fire because you're going to exceed the ampacity of that bus bar. You're going to be putting more than 200 amps on that bus bar when it's only rated for 200 amps. Code says, actually, that's okay to a certain extent. And what this is, and there's a lot of language on the left there, but what this is saying is that even if we have 200 amps coming in from grid, we're allowed to put 40 amps of back-fed power on the bottom of the load center, and we can feed 40 amps here and 200 amps down there, and we don't have to worry about exceeding anything because the 200 amp bus bar is going to be fine. You do always have to put it at the bottom, the breaker at the bottom of the load center. So you're kind of feeding it from two separate ends so you don't get hot spots on the bus bar. And you got to put a little warning sticker on that 40 amp breaker saying don't move this breaker, and put it somewhere else in the load center because you want it to be on opposite ends. And here's an example of that. This was a system. This is a real life system. We came out to the home. It had a 200 amp main breaker. The load center was rated for 200 amps. And that meant that we could only put a 40 amp breaker on it. Well, we wanted to put a 50 amp breaker on it because we wanted to be able to feed, not necessarily back feed 50, but to be able to feed 50 amps into a Solarc. And then also be able to feed more than 40 amps out to a load center where we knew we were going to need something that needed more than 40 amps worth of output because it has to pass through. What we ended up doing is upgrading this load center to a 225 amp bus bar, which then allowed us to put up to a 70 amp breaker in there. And we were able to feed through more than 40 amps through that Solarc and back down to that load center. I'm not sure why we didn't go with the 70 or 60 here. I think maybe this was existing conductor here and that was only rated to handle 50 amps. And we didn't want to exceed the ampacity of the wire here. What's interesting is that there's some new technology out there in these hybrid inverters. It's called PCS control, which essentially says that the problem is that we need to be able to draw a lot of power to be able to power backed up load centers. But we don't necessarily need to push back a lot of power to the load center. So these inverters now are smart enough and are approved now to say that, look, we could have put a 50 amp breaker here and not had to upgrade the bus bar, but we're never and draw 50 amps, which is fine, right? Because if we got 50 amps here and people turn on a bunch of loads, we're still protected by the breaker. We can always draw whatever we want, 50 amps or more, but the inverter's smart enough to know never to backfeed more than 40. It's called PCS control. We could probably spend the whole hour talking about that, but let's move on. Generators. So this is another problem here. We're looking at a wiring diagram of a Solarc 15K. Up here is grid. We got our meter. This example had an existing generator on site. So normally when we came out to the site, we would have grid, a meter, a transfer switch, and then right out of this transfer switch, it would go right down to this load center. Everything on the left is kind of being added. So we added a hybrid inverter. We added a Solarc. Now, grid comes through the meter. Normally, this transfer switch be in the vertical position on normal operation, and the power would flow through into the grid port, right out of the load port, and this is rated for 200 amps on the 15K. We would come right back out of the load port to our load center, power our backed up loads. We got some DC coupled solar, we got a battery bank. If grid goes down, within milliseconds, the Solarc will disconnect us from grid. This transfer switch remains in the vertical position. It's not going to switch yet. If the batteries start to get low, because we don't have solar at all or it's cloudy out, the Solarc will signal to start the generator. The generator will start up and then send a signal to transfer so that the transfer switch will look like it is now in this diagram, where generator power will come in, feed up into the grid port. And as far as the Solarc is concerned, it will recognize it will recognize AC coming into the grid port. We use that to charge our batteries and then start powering our loads. There are some settings in this Solarc and other hybrid inverters that you could tell that this is what's happening, is that there is a generator on the grid port, so that if the solar does happen to come out, say the cloud goes away, it's not going to try to backfeed the generator, the DC coupled solar. But what happens though if we have AC coupled solar on this system? Remember that when the grid goes down, the solar or the other hybrid inverters form a grid, and the AC microinverters or string inverter recognizes that as grid and starts operating. And when the batteries get full, the hybrid inverter can change the frequency of the AC sine wave to shut off the AC coupled microinverters. But when we have a generator running, or when we're connected to grid, the solar is no longer grid forming, it's grid following. It's following the grid, the utility grid, or it's following the generator sine wave. So we lose that ability to adjust the sine wave. And if we don't put in something like a lockout module, it's possible that if the generator is running and the AC coupled solar is producing, that your AC coupled solar could backfeed in the generator and start to damage things. Now, I'm going to get deeper into this topic at NABCEP when I give a generator talk, and I also do other webinars where we'll get deeper into this topic on generators. Now, there's a lot here. What we're looking at now is the grid boss, and I also recognize we're about 4 minutes, so I want to respect everyone's time. The EG4 sells a hybrid inverter, very similar to the Solar. And each of those can be connected to a battery. Each of those should be connected to a battery. You don't need 3 of them. You can just have one. And then there's this grid boss. It's kind of like a fancy transfer switch, all AC loads coming in and out. We can connect hybrid inverters here. We can have backed up loads here, non-backed up loads here. We got our grid coming in and our gen port, right? You could think of this as the grid port, the gen port, and the load port. But what's interesting with the grid boss is that it gives you additional gen ports or additional smart ports where we could bring in AC coupled solar. We can bring in or have output loads here. And what's interesting about how the grid boss works is that if the generator starts, and this example doesn't show this, but this relay would be closed, the relay to the AC coupled solar would open up. So that previous picture where I showed you had to have something like a lockout module or a relay, it's actually built into the grid boss. And we are going to be hosting another webinar later this month where we're going to get deep dive into how this grid boss works and a lot of the advantages that come with it. We make a line of air-cooled generators, anywhere from 13 to 26K. They're all propane or natural gas. They don't derate on natural gas. We also make a line of commercial generators as well. I'm really excited for this battery. It goes together quickly. I put together a number of the systems now, and they are able to be connected to the EG4, the Solar that you see in this picture, as well as some of the many other hybrid inverters. It has a base on the bottom, up to 3 modules per stack, and then it has a controller up top. That has a light, right, to show you the status or the charge of the battery. And also is where the DC outputs go to the hybrid inverters as well. They're all held together with alignment pins. And these are some of the SKU. Again, the energy track is optional on the right-hand side. If you haven't done a system yet, we'll give you $1,000 off your first system. If you have done a system, we'd invite you to join our installer program. There's a quick course you have to do, a quick test. We'll allow you into the system that allows you for rebates. But more than that, you can get trip charge reimbursements. We'll put you on our installer map, and we'll send you some free swag as well. There's a lot of courses on the Power Academy, which is our learning platform. Some of them are self-paced e-learning. You can also register for in-person courses. And we also have what are known as some live webinars, similar to what we're doing here today as well. Thank you, everyone, for joining. I know that was a lot, and I went really quickly. If you want to have a deeper dive, check out some of those other trainings. If you're going to be at NABCEP, and you want to join our battery summit, email me, let me know. If you want your NABCEP credits for this, email energystorage@BASCO, B-A-S-C-O, that stands for Briggs and Stratton Company.com. My personal email is up there. I'd prefer if you need something quick help, use the personal email. If you want your NAPCEP credits, send it to energystoragetraining@basco.com. Everybody will get a recording and a copy of this slide deck. Thank you, everyone, for joining. If you want to jump, get back to your day, great. If you got any questions, put them into the Q&A now, and we'll see everybody next time. All right, no questions. All right, take care, everyone.